All right, so now some applications of our derivatives. So if you remember, for our derivatives, f prime of x, positive means we're increasing, and f prime of x equals a negative means we're decreasing, and that the derivative is basically our slope that we're looking for, change in y over change in x. It's an approximation to our slope. It's the limit of our difference quotient, so it's a limit of our slope. So it is estimated that t years from now, the population of a certain town will be this little formula. So if we plug in any value of t, it'll tell us the population of the town, an approximation of it. So someone has gone through, looked at the data, and says it looks like a parabola, and they've done a regression, and it's given them this function. All right, so it says, what is the rate of change in population in the town at 5 years? So we can tell here that we want the instantaneous because it wants at 5 years. So if we take the derivative, this is now our rate of change at any given year that we plug in. So if we plug in 5 years, we end up with 210. Now we need units on here. And so our t is years from now, and our p is population. So we want to write that. P equals population. So we're talking about people here. And t equals years. So if we find p prime, this is approximating the change in p over the change in t, because our p here is our numerator, and our t is the bottom, the denominator. So this is going to give us population per year. And what we're talking about with population is people per year. And so if we put that on here, now we put people per year, it now gives us our rate of change. So we're talking about at 5 years, we're expecting 210 people per year. So to go from 5 years to 6 years, we would expect a 210 growth. So now, is the population increasing or decreasing? Well, our p prime of 5 is equal to a positive, so that means it is increasing. If it had come out to be a negative, we'd know that it was decreasing, but it's increasing. So it looks like this. So here's our formula, x squared plus 200x plus 10,000, right there. And so if I put it at 5, you can see there's our slope. So we're at 11,025 at 5 years, and they expect a 210 growth to 6 years. So that would be 11,235. And if we move it to 6, come on, go to 6. I'm trying here. There we go. Moving to 6. See, 11,236. So we're one off, but it's a pretty close. This looks pretty linear here. You can even see our slope of our tangent is pretty close to the graph itself. It's a little bit off. So if you zoom in, you can see there's a slight difference. See, it does deviate a little bit. It's the slope of our tangent. It's only touching at one point, not multiple. So there you have it. So if they want to know the rate of change at a certain point, they want the instantaneous change in population. Whatever p is, that's the numerator, and whatever's inside is the denominator. So you can also look at it this way. This is numerator, denominator. So it's people per year. People per year. So at 5 years, 210 people a year. All right. So now that we've done with the derivative, what we're going to do now is just interpret. We know how to find derivatives, so we're going to be able to get through 2 more examples fairly quickly by just interpreting. So the temperature T in degrees Fahrenheit of a cold yam placed in a hot oven is this formula, where T is time in minutes since the yam was put in the oven. So with all word problems, you want to write out the function, and then you want to tell everyone what everything is. So T is time. And then you want to put its units. The units are very important because we're going to need them in our answers. And our capital T, which is F of T, is our temperature. And that's in degrees Fahrenheit. Okay, so now what is the sign of F prime of T? Well, F prime of T, that's going to be our change in capital T over change in little t, approximate. And so F here is our temperature. So when you see F prime of t, they're asking you, what is the sign of F prime of t? They're saying, how is your F changing? So how is our F of t, which is capital T, changing? And if it's asking for the sign, is it positive or negative? That's our question. Okay, so what does T stand for here? T is the temp of what? It's a cold yam, and we're placing a cold yam in a hot oven. So if you place a cold yam in a hot oven, what will happen to the temperature of the yam? It will go up. Yeah, so the temp will go up. And if the temperature is going up, that means that it is increasing. So our F prime of t here would have to be positive because the temperature is going up. The yam is going to increase its temperature because it's being placed in a hot oven until it gets to an equilibrium, and then it would be constant, and then you turn the oven off and it'll go down in temperature, decrease. But for right now, it's just positive because the temperature will go up. So now what are the units of F prime of 20? So let's write what it is. This is F prime of 20, and the units on 20 would be minutes because that is our little t. So they're really just saying our t here is 20. So what is the temperature? What it's asking here is, how is the temperature of the yam changing at 20 minutes? And so I like to write it out with the units. This would be change in capital T over change in little t, and it's an approximation of that. How is our temperature changing per little? Okay, so if we go back to our units, right, the capital T represents the temp. And what we want to write is the actual units, so degrees Fahrenheit. And the little one, the little t, is minutes. So what are the units of F prime of 20? They're degrees Fahrenheit per minute. So now let's put all this together and find out what the practical meaning of this statement is with units. So F prime of 20, the 20 would be minutes, and you always put units on them before you make a practical meaning of a statement. So once you have units, everything's going to make sense. So this 2 then is what we would have at the end. It's going to be this right here, degrees Fahrenheit per minute. So then what the practical meaning of this is this whole thing is about what? So whenever you do any interpretation of something, you want to first start at what the whole problem is about. And so it's the temperature T of a cold yam. So let's put it way over here. The temperature of a yam at 20 minutes. So you can see I'm just writing it. The temperature of a yam, that's it, at 20 minutes is approximately increasing. How did I get increasing? That's right, because it's positive, by 2 degrees Fahrenheit per minute. So what this means is by finding the derivative, at 20 minutes, we can take out whatever temperature is. So let's just say the yam is 350 degrees at 20 minutes. Then at 21 minutes, we would expect the yam to be 352 degrees. It would be a 2-degree increase. So that's what this means. When you see a derivative, it's telling you the approximate change that we're going to get. So this is about the temperature of a yam. So the temperature of the yam at 20 minutes is going to increase by 2 degrees Fahrenheit per minute. And we don't know if it will or not. Remember, with ours, this could be the temperature increase of the yam, and we're here, and so it's going to be an offshoot a little bit, but it's an approximation. All right, one more. So it says the time for a chemical reaction, T in minutes, is a function of the amount of catalyst present in milliliters. So T equals F of A. So again, T here in our function is minutes. It's the time, and it's in minutes. And A, that's the one we're inputting, is the amount of catalyst. In milliliters. So our units are milliliters. And now we can interpret stuff. So whatever's inside, that's our A. You can see it right here. That's A. So what are the units on 5? 5 is milliliters. What are the units on 18? Well, that would be minutes. So it makes it quick. Once you write them out, you can see where they're located. So T is 18. You can see that here. So T is minutes. So 18 would be minutes. A is the inside, right? It's our input. And so A is milliliters. So what does this statement tell us about the relationship? So now we rewrite what it has there. 5 milliliters equals 18 minutes. And then we interpret it with this. So reading the problem, it says the time for a chemical reaction, right? And then we just write it. So the time for a chemical reaction with, and you can say with or for, whatever you want here, for 5 milliliters is 18 minutes. So with 5 milliliters of catalyst, you have to add into it to make sure it makes sense. So if they're putting 5 milliliters of catalyst, the time for a chemical reaction will be 18 minutes. So a lot of different ways to write it, but I like to just say the time for a chemical reaction with 5 milliliters of catalyst present is 18 minutes. And so if you use 5 milliliters of catalyst, 18 minutes to have a chemical reaction. All right, so now let's do our derivative. So this would be F prime. And again, the units for 5 are milliliters because it's the input. But we now need to write out what our F prime would be. So again, this would be change in T over change in A. So because T is our Y, it would be change in T over our input X would be change in A. And then we write our units for that. So this would be minutes per milliliter. So that's our units for F prime, minutes per milliliter. So what are the units for 5? It'd be 5 milliliters. And then what are the units for -3? Well, our F prime is milliliters per minutes per milliliter. So that would be -3 minutes per milliliter. So what does that statement tell us? So let's write it out. F prime of 5 milliliters is equal to -3 minutes per milliliter. And so we go back and we start with the same thing. So the time for a chemical reaction is, forgot the time. We completely forgot that, the milliliters. So remember, it's the time for a chemical reaction at or with 5 milliliters of catalyst is changing, or we should say decreasing, at a rate of 3 minutes per milliliter. So let's make sure this makes sense. So it says the time for a chemical reaction with 5 milliliters of catalyst is decreasing at a rate of 3 minutes per milliliter. So what this means is if we add an extra milliliter, so we change this from 5 milliliters to 6 milliliters, the time for a chemical reaction will go down by 3 minutes. So right now with 5 milliliters, we're at 18. So 5 milliliters, it takes 18 minutes. So if we're doing 3 minutes per milliliter, that means if we increase this to 6 milliliters, the time will go down by 3, and so we would expect it to be 15 minutes. So we expect with this approximate change here that it would be 15 minutes for 6 milliliters and so on and so on. So the time for a chemical reaction, this right here, and this is a rate in this case, so this is now our rate, with 5 milliliters of catalyst is decreasing, and I got that from the negative, at a rate of 3 minutes per milliliter. So that's all you have to do to interpret these.